Today, our topic is white noise in Euclidean space. The topic is white noise in Euclidean space. So, this is our topic for today, and before going to the actual topic, where we have to represent the white noise in Euclidean space, let me recall the concepts of three-dimensional Euclidean space, which you learned earlier in my previous lectures. So if we recall that one, we can represent our signal in three-dimensional space, where these x's are the three psi 1 of t, psi 2 of t, and psi 3 of t. And I mentioned earlier that any point here in this three-dimensional space will have a vector with three components, for example a, b, and c, and these three components, or these three coordinates a, b, and c, they represent the image of this vector, which is a position vector, the image of this vector on x-axis, y-axis, and z-axis. Here the x-axis is represented by psi 1 of t, because we already mentioned that if we have three orthogonal signals, psi 1, psi 2, and psi 3, we can construct a three-dimensional Euclidean space, and we can represent our signals in this three-dimensional Euclidean space. So any signal s of t, suppose this is the vector for s of t, this vector is for s of t, or I would say that this is these coordinates are for signal s. So any vector s of t can be represented as a linear combination of these xi 1 of t plus b times psi 2 of t plus c times psi 3 of t. So this is how we can represent our signal in three-dimensional signal space. Well, these as an example, I mentioned that these three signals, psi 1, psi 2, and psi 3, can be 0, 1, 2, and 3. So we can say that, okay, psi 1 is this one, psi 1 of t. Similarly, we can represent psi 2 of t, and as I mentioned earlier in my previous graph, that okay, psi 2 of t exists between this one, 1 and 2, right? This is for psi 2 of t, and psi 3 of t, which I mentioned earlier, that our psi 3 of t can be represented in the same way. I'll write over here. So my psi 3 of t is a pulse from 2 to 3. So these are this is psi 3 of t. Now I can represent s of t. What actually s of t is? It is the scaled version of psi 1 of t plus the scaled version of psi 2 of t and the scaled version of psi 3 of t, and these scaling factors are given by a, b, c coordinates. So if you have these scalars available, you can just add these signals. You can add these signals, and you can construct your s of t. So this is what we did earlier. Now we are not limited to just three-dimensional space. We can have any number of dimensions. For example, if in the above basis functions, or psi 1, psi 2, psi 3, I have another one. Suppose I have another one which is just like this one, right, from 0 to 1. So this can be considered psi 4 of t, right? Similarly, I can have from 2 to 3 another signal, this one, and this can be considered as psi 5 of t, right? Similarly, you can construct n-dimensional signal. If you have n dimension, n basis functions, or generally I would write that S of t can be written in n-dimensional signal space by just considering as, like, we can write it this way. Let me use the same notation which I have mentioned earlier. We can write it a times psi 1 of t plus b times psi 2 of t, and it can be any dimension plus you can say n times psi n of t. Now this is the signal in n-dimensional Euclidean space, n-dimensional space. This is a signal representation in n-dimensional space. If you want to represent it as a vector, so the signal vector could be written as a, b, and so on, n, right? We can represent this is the signal vector for n-dimensional space. Now usually we in 4G of wireless communication, if you see, we have just two dimensions, psi 1 and psi 2. So I would restrict myself to these two dimensions, and with the two dimension we will discuss the modulation schemes. But for today, as white noise, as I mentioned earlier, it is a random process, so we can consider it as a sample from the random process, and the white noise signal can be, if I represent my noise by n of t, so the n of t, which is the noise signal, because whenever you keep this in mind, just let me recall the concept that whenever you transmit some signal s of t from your transmitter, and you have a receiver, a distant receiver, when this signal is transmitted to the receiver, you would receive a signal which, in the absence of noise and other channel effects, should be s of t, right? Because this is what you transmit. But at the digital receiver, you will always see that there is a component, additive component, which is this one, n of t, and this is called the noise. And the noise model is, we already discussed the model for this noise, that Gaussian, it is Gaussian. That is why we call it additive white Gaussian noise. So if you observe your noise, n of t is a random process, and we can represent noise in the signal space. So we represent noise assuming that the noise is it is in all the dimensions, so we can represent n1. We can just write it as a linear combination of, like this, n1 psi 1 of t, similarly n2 psi 2 of t, and up to the last n7 psi n of t. So this is just the representation of noise signal in n, representation of noise signal which is an n-dimensional signal. I represented this as a linear combination of these basis functions, assuming that I have a set of basis functions, psi 1 of t, this is the set of my basis functions up to psi n of t, and all these are orthogonal and their energies normalized to unity. So we can represent our noise signal this way. But when the noise is in n dimensions, we usually are not concerned with all the dimensions. As I mentioned earlier, that in 4G we have only in 4G we have the our signal of 4G is just two-dimensional, so we restrict ourselves to two dimensions, and suppose our signal vector is given by just two-dimensional as a linear combination of psi 1 and psi 2, so we would be interested in the noise which is corrupting our actual signal. So from the above expression I can represent my noise, which I can represent my noise as I can represent my noise as the noise of interest, which I would mention by n cap of t, and the noise which is in other dimensions n tilde. So this component is the noise of interest, and I would say that okay, my n hat of t, it's n hat of t, n hat of t is n1 psi 1 of t plus n2 psi 2 of t, right? This is my noise which is of interest, because my signal is just two-dimensional, and the remaining n hat of t, this can be written as n3 of psi 3 of t up to n the 7 psi n of t. So this is the remaining, or I can also write n tilde irrelevant noise as the actual noise minus the relevant noise of interest. So this is which is irrelevant. Now this is irrelevant noise. We would be concerned about this component which is corrupting our signal. Now if you consistent with our previous to be consistent with our previous discussion, we can find the component of noise in psi 1 direction and psi 2 direction, or generally I can write that the component of noise in the direction of ith basis function is just the dot product of the noise signal with the ith basis function. What's the dot product? As I mentioned earlier, that you always, if you have a vector, because this now n of t is a vector, so we can represent our n as n1, n2, and so but only we are interested only in these two components because our signal is two-dimensional. So we would be interested in n1 and n2, and n1 the image of the signal over psi 1 which would corrupt our actual signal can be found by the dot product from the above expression, the dot product of the noise signal with psi 1 of t. So this is the similarly we can find n2, n sub 2. Now with this knowledge and having our previous discussion on the signal space, we can represent a noisy signal in the signal space. Suppose I have two dimensions only, all other are irrelevant. Okay, suppose I have a signal in 2 dimension and I give you the signal points. Suppose my signal points are given by this vector notation, which is suppose 1 and 1, right? So you can easily plot this signal somewhere here, right? Somewhere here, which is 1 and 1. But if I say that my signal is corrupted by noise, and I give you the noise vector, which is a noise vector which is suppose 0.11 and suppose 0.23, something like this, any random, because noise is random, so it would have some random values here. So if my signal is corrupted by this noise, I would represent the noise signal 0.11. 0.11 means actually what will happen to my received signal, it would be signal plus noise, right? So the signal plus noise coordinates would be 1.11 and 1.23. So this will be a coordinate for signal plus noise. So the noisy signal can be drawn on 1.11 is somewhere here, right? Suppose somewhere here, and 1.23 is 1.23 on the graph is somewhere, suppose here. So I would draw the new point, the noisy point here. So this would be my signal plus noise. This is the vector notation for the signal point for a noisy signal, right? And if this is, suppose these are 0.11 is negative and this is positive, suppose this is positive, then it would be somewhere here. It would be somewhere here. The new point would be here in the Euclidean space. And suppose both are negative, this one is negative and the other one, this is negative and the other component is also negative. So this point would fall somewhere here. So the signal which you are transmitting, which is S11, which should actually be here. It can, depending upon the noise sample, it would be somewhere in the first quadrant. It would be somewhere here. It can be this one, it can be this one, it can be this one, depending upon the noise symbol. So remember about the noise which is added to this signal. So I expect that this is enough for the effect of noise to our signals, and you should be able to draw white noise in Euclidean space also, because if you want to draw this one, so just if I say okay, just draw noise in Euclidean space, so and I give you this vector, so you should be able to draw it. 0.11 would fly, suppose this is plus, both plus, for plus we have this noise. We can find the noise vector, which is 0.11 somewhere here and 0.23 somewhere here. So our noise vector, noise symbol is here, right? This is our noise symbol, and we can say the position vector of noise is this one. This actually add up to our signal vector, which is this one. When this add up to our signal vector, you can have another resultant vector, and that can be represented by position vector of these noisy points. So that's I guess enough for the white noise in Euclidean space. Hopefully you get the basic concepts now.